Okay, so this should be a short video to clear up some vocabulary words that I think are maybe have not been made clear yet in any of the videos. And even though we may discuss them a little bit in class, they're not explicitly spelled out. So first of all, is the word differentiable. So when we ask is something differentiable, that means can you take the derivative of it? So if I'm thinking about a function and I want to know whether it's differentiable or not, there's two things that'll make it not differentiable. A function is not differentiable, so f of x is not differentiable. First of all, if it's undefined or there's a discontinuity. So if the function's undefined, that means obviously I can't take a derivative at that point. So a function could be differentiable for the most part, but there's just like maybe 1 or 2 points where it's not differentiable. Like, for example, f of x equals 1 over x. I can take the derivative of that function in general, but it has a discontinuity at x equals 0. That means it's not differentiable at x equals 0. Okay, the second reason that a function is not differentiable is at what we call a cusp, or a sharp point, or a pointy point. And for example, f of x equals absolute value of x. If you look at the graph of that thing, we know that it looks like that. And if I ask you to find the derivative of this graph, well, we don't need any fancy formulas, because remember, derivative is just rate of change, aka slope. In this case, the slope is constant. So the derivative over on this side is 1, and the derivative over on this side is -1. So the question is, what happens down here at this point, at 0? Well, if you're coming from this way, it appears that the slope is -1, but if you're coming from this way, it appears the slope is +1. It can't be both +1 and -1. So what we say is that there is no slope, or the slope is undefined there. We're not saying the slope is 0, we're saying that the slope is undefined. And that is what we call a cusp. So cusp, or anything that are kind of a quick change. For example, you could have a graph. There's a lot of graphs that looks like this, where they come in and kind of hit and then ricochet off, as opposed to you've seen graphs that look like this. They come down and ricochet off like that, right? That's not what we're talking about. We're talking about a sharp change in direction. And they could even be less subtle. Like you could have a graph that comes up like this and then kind of goes like that. Still, there's a sharp change there. It's not a gradual, smooth change. So anything that looks like that's a cusp would mean that the function is not differentiable. Another example of a cusp is in a piecewise function. You could have a function that looks like this, another function that looks like that, right? I mean, that's part of the piecewise function. Well, the function would not be differentiable at 0 in this case, because that's a sharp point, because it just comes to an end. There's nothing on the other side of it. Well, there is something on the other side, but it's down here. So that would be another example of a cusp. So when you're being asked whether a function is differentiable or not, you're asking, does it have any discontinuities, and are there any sharp points or cusp? So you would say it's not differentiable at the discontinuity, or at the cusp. So that's differentiable. Then the second thing I want to talk about is tangent line. So I've mentioned tangent line several times. Just wanted to make clear that a tangent line is actually just a line. So it can be described like as in y equals mx plus b. So if I'm looking at a function that looks like this, roughly, here's my f of x, and I tell you that the derivative is 2 at the point. I'm going to redraw f of x. Let's say it goes like this. let's say that the derivative is 2 at the point 2, 2. Let's say 2, 3. So now I'm going to make it go through 2, 3. Okay, so if I tell you the derivative is 2 at the point 2, 3, then I ask you to write the equation of the tangent line at that point. So that means we're going out here to this point and we're drawing a tangent line, right? Line that's basically representing the slope at that point. So the cool thing is, because the tangent line represents the slope at that point, that means the slope at that point, or the instantaneous rate of change, is the slope of the tangent line. So if I wanted to write the equation of that line, I would just I'd use this handy little slope, or handy little equation formula. Maybe you've seen this before, maybe you haven't. This is the point slope form of a line, because I'm just trying to write a linear equation. So I'd go y minus the y coordinate is equal to the slope times x minus the x coordinate. And that would give me the equation of the tangent line. So in class, we've talked about tangent lines and secant lines. The tangent line is a line that represents the steepness, or represents the slope of the at that point. So to be more clear, we could say the instantaneous slope of a function is the slope of the tangent line to the function at the point of tangency. So again, if we just draw a picture, you got a slope, you got an equation like that, you got a tangent line like that, and we're talking about that point right there. So the slope of this line, that's the tangent line, the slope is the slope of the function at that point. All right, so that's just a couple things I wanted to clear up. I wanted to make this one short, so hopefully this is helpful.